Hey everybody, welcome to CS302 assignment 4. And for this assignment, we're going to implement this Huffman prefix code algorithm. And this is essentially, this prefix code is a way to compress data. So for our assignment, we're going to be given a quote-unquote compressed file, and we're going to decompress it into the original format. Now, when I say quote-unquote is because it's not going to really be truly compressed, because we're going to read a series of ones and zeros as binary representation, and we're going to convert it into the characters, but each 1 and 0 you're going to read is not going to be 1 bit. It's impossible to read 1 bit of memory, so everything is 1 byte, so there's really not going to be actual real compression or saving memory, but we're going to pretend that when we read our ones and zeros, we're reading a compressed data, and then when we convert those ones and zeros into actual letters, we are going to decompress it. So we have to, of course, go over Huffman code and go over what prefix code means. And this image right there is, this is a device used for Morse code, which Morse code is sort of a encoding system of using different sounds or frequencies. I'm not sure the exact logic of it, but I remember from watching the movie Independence Day, they use Morse code to send signals. So you can, of course, send a signal, a message through Morse code, and all these individual beeps and symbols represent a letter. So you could transfer data like that. It's like texting back in those old Nokia phones. It's kind of similar to that in a sense. I guess that's probably the best way I can describe that. So also another interesting backstory with Huffman coding is this person was either a master's or a PhD student in MIT and in the 50s, and believe it or not, this algorithm was actually his master's or thesis for his PhD. I'm not sure if it was a master's or a PhD thesis, but pretty interesting for a student, for a grad student, to develop an algorithm that's actually widely used. So anyway, now let's go ahead and sort of discuss our binary tree class. Then, of course, I will trace out an example of how this Huffman coding works, then go over the input-output, and so forth. Let's get to it. Okay, so here is our binary tree class as a BinTree, I suppose, which I guess binary tree would have been good enough, but BinTree is also just fine. So we're going to have this struct BinTree node defined in our BinTree class, and every node will have a letter frequency and a pointer to its left and right child. We will go over letter and frequency fields when we go into an actual example of this Huffman coding algorithm. So for now, just bear with me, but I will explain this in more detail later on. So I could have used a struct in our BinTree node, but I guess I didn't really put one in there, and it's not really a big deal. It's not going to save us too much code because we're not going to be inserting nodes in too many spots in our code, so it's not a big deal really. So it's not going to really cause any problems. So there we go. There's our BinTree node. Then we have this BinTree node star root right here. So this is going to be, again, we have to have a root pointer in our binary tree class because we have to know exactly where our starting point is going to be for our binary tree. So remember, the root pointer is going to serve similar to the head pointer for a linked list. Now I'm going to go over these private functions in a second, but these will be actually used in our public member functions. So let's go ahead and go through the rest of our class. So we have our default constructor, and I have all the definitions, I have all the actual PDF write-up of all the functions here, but I'll talk about it here in this video. So our default constructor sets a root to be null. The second constructor here is going to only allocate just a single node to the root. So it's not going to recursively build our trees. Luckily, this program is not going to require us to have to recursively construct a binary tree. So again, it could make things a little bit easier. So of course, this function just allocates a node to the root, sets the root nodes left and right to be null, and it will set this character to the letter field of the root node, and it will set this integer to the frequency field of the root node. That's it. Now, the second constructor, this is going to be used to combine two trees together. So we're going to pass in a reference of two trees, and we're going to combine them into our current tree, essentially. So we pass in two references, and we combine them. This is going to be used when we're combining trees together, when we're going to have to construct our Huffman coding tree. This construct will be used quite a bit to constantly merge two trees together. And it's actually a very simple function as well, so give a little bit of a hint to that later on. Then we have our destructor, which will deallocate the tree. The destructor will just simply call this function destroy tree. This is going to be called in our destructor. It's going to be a single line code in our destructor. We're going to call destroy tree and pass in the root. Now, the hint for deallocating a binary tree, you're going to have to deallocate this in a post-order type traversal. So it'll be literally the post-order code in class, but instead of couting our arrow data, maybe delete R is a good idea. Think about that. Think of what if that's going to work correctly. But I mean, it's not really too complicated functions. I don't mind giving that away here in the video because it's not so hard. Then we have our get frequency. This function returns a frequency field for the given. So it's going to return the root node's frequency. So we have essentially the root pointer in our binary tree class. This function returns the root node's frequency. And then we have the only really hard part. It's going to be the recursive function for our class. This is going to be either a pre or post order traversal. It's called prefix, but don't get confused. It might be pre-order, it could be post-order. You don't know, so just be careful. This function, we're going to pass in a letter. It will traverse the tree and find the leaf node with the matching letter, and it's going to return the prefix code for that. So this function right here gets called in main, and this function internally is going to call the overloaded get prefix code. We're going to call the function get prefix code, pass in the root, pass in the letter, and this function is going to recursively traverse the tree, find the node, the leaf node that has a matching character, and then recursively you're going to have to build the prefix code. So I will, of course, draw an example to help you see how this works, but it's going to be used mostly once we have our complete Huffman tree constructed. Then we're going to essentially create every character's prefix code. So I'll go over the actual recursion or give you an idea of it when I go over the Huffman coding algorithm. So anyway, that's the quick rundown of our class. So the next thing I'm going to do is I'm going to now talk about the Huffman coding algorithm, which of course I'll go over how we will essentially use these constructors and the function get prefix code to get our prefix code for each letter. So let's go ahead and get started. So let's go ahead and first just discuss what is prefix code. So basically, you probably learned about this in your systems programming class, otherwise known as assembly language class, where every letter in the ASCII alphabet, I suppose, is going to be 8 bits to represent each character. So if you want to have, let's say, A, B, C, or let's say, I don't know what string I have here. Let's say if I have like B, A, C, B or something, well, we have to essentially have 8 bits for the first letter, 8 bits for the next letter. We've got to count every 8 bits to construct each letter. And doing that is going to require, a lot of characters, a lot of bits needed for each character. But notice this example right here. We see here, we only need 3 bits to represent A, 1 for B, and 2 for C. So we already kind of compressed the data a little bit. So if we're given, let's say, this input right here, this is going to be our compressed input. We can construct our original message from this by using a prefix code. So the first character we see is a 0, and it matches that prefix code right there. So this is going to be the letter B. So instead of using 8 bits, we had only 1 bit needed to be able to extract letter B, which would have, so it basically went from 1 bit to 8 bits, if you will. Now, in fact, it's not true because really each character of the string will be 1 byte, but just pretend for a second that the zeros and ones are just bits. Then we see that 1 bit was used to represent letter B, not 8 bits. Now over here we see a 1. I used red. We see a 1. There's no prefix that has only a 1. Okay, let's see. We have 1, 1. There's no prefix code with 1, 1. Then we have 1, 1, 1. Okay, I see there is one of our prefix codes that matches that. So that's going to be the letter A. So again, we use only 3 bits to essentially represent an 8-bit ASCII character A. And now again, we go through the same process. So 1 by itself, there is no 1 prefix code. Okay, let's go ahead and look at 2 next. There is no prefix code with just 2 ones. With 3 ones, okay, we again find a match, which means that, okay, that's going to be letter A. And then, now if we continue, we see 1 by itself, and there is no 1 by itself. Then we have 1, 0, and we do have a 1, 0. It's going to be letter C, so we can represent those 2 bits to be C. Then at the end, we have a 0 all by itself, which is going to be another B. Hope this hope is not a bad acronym or a bad, I think it's okay. I never heard of anything like that, so it should be fine. So there we go. Using those few bits, we don't have to use, normally we'd have to have 1, 2, 3, 4, 5. We'd have to use 40 bits because we have 8 bits per letter. We need 40 of these ones and zeros to represent this, but notice we have much less than 40 bits to represent this string. So that's what prefix code is all about. So once we have a prefix code and we take our compressed data, we can easily decompress it by we just go through our strings, and when you finally find a match with one of our prefix codes, we extract, we put the actual original character there. So hopefully that part is not so bad. So you'll have to actually write a program that will do this. Now, prefix code, you're wondering, how do we know where it cuts off? Because for regular ASCII characters, every 8th bit is a new character. And it's because they are valid prefix codes, as in these do not overlap at all. That's why it works. Now imagine for a second the following. Let's say we had a string like this, where we had, let's say, our character prefixes like this. I have A, B, and C again. Let's see if I have, I'm going to maybe put 1, 0. Then I'll put 1, then I'll put 0. So here's a really good example. So if let's say we have this prefix code, this could cause a problem. Let's say we have the following string. We have, let's say, 1, 1, 0, let's say. That's a very simple example, but why not? So here's a problem. So is this going to be 1 and then 0? So it's going to be A, B? Or is it 1, 0, which is going to be a C? In this case, it's ambiguous. So this would not be a valid prefix code because none of the characters can be subsets, because the problem here is that 1 and 1, 0 and 0, it creates a problem. But notice over here in this example, there is no scenario. There's no subset, like there's no pre-subset, I guess, if you want to call it. So none of these overlap. So we have 1, 1, 1. We know for sure it's an A. Anything that comes after this would be a new letter. If you see a 0 by itself, it has to be a B because there is no other case where it's like 0, 1, and we have a 1 by itself or whatever. So it will never cause ambiguity if you have a valid prefix code. And this Huffman coding algorithm, it's going to ensure that there will be no overlaps like we have in this case. So that's going to be just our very simple Huffman coding. Or not really Huffman coding, but this is a very simple way to just understand what prefix code actually means and how to take a string and be able to match it against our prefix codes and extract the original letters out of them. So now what I want to do is I want to go over, I guess I'm going to go over the contents of main right now. So I want to go over the actual Huffman coding algorithm. Let's go ahead and discuss that. So this is going to allow us to basically construct these prefix codes for various letters. Let's go ahead and get started. Okay, so suppose we have only these letters we're going to be working with, and these are going to be the frequencies. So yes, how many times they appear in some text. These are 100% made up. I just made some make-believe frequencies. And the frequencies are going to be used to determine the prefix code. So the idea is that the letter that occurs many times, we want to have fewer number of prefix characters for that letter to really further be able to compress the file. And the ones that have a lower frequency, like E, for example, you want to use maybe more characters to represent E's prefix code. But anyway, the idea is given to you here in a PDF. We're going to want to create either a vector or a list of binary trees. Now, I have a list of binary tree references, and the reason why is it makes it easier to link link up trees essentially. And I'll sort of give some idea for how you would code this, but you want to have a vector or a linked list. I would just say use a vector instead. It's a little bit easier to work with a vector, but either one is going to be fine. And of course, use any of the library functions for vector and list is okay to use here. So just to make life a little easier, we kind of more or less graduated from linked lists and data structures. So now at this point, you may as well use the built-in linked list or built-in vector just because it makes life a little easier. So the very beginning, what you're going to be doing is you're going to have to insert all of these references into our forest. And I called it a forest because, well, we're going to have a collection of trees, and a collection of trees is what a forest is, I believe. So yeah, we're doing more. Is it a CS class or is it a biology class? I don't know anymore, but I guess a set of trees would be a forest. So, okay. So the first thing you want to do, you want to insert elements into our forest. So for example, I'm just going to show you a quick example. How would you insert a binary tree with only one node at the root, A3? What you can do is like this. So for the forest, you can say, I'll use green here for now because it makes sense, right? So forest dot push back. I'm going to push back a new BinTree. I'm going to pass in the letter A and 3. So what does the new keyword do? It's going to allocate a object, a BinTree object. It will assign the, it's going to allocate a single root node to this object. And that root node's character will be A, frequency will be 3, and we're going to assign the address of this node to the first position of this forest vector. So in other words, what's going to happen is we're going to have this arrow. I'll use maybe the arrow object here. Why not? Looks nicer. We're going to have this arrow that points to the object. Now, this is not the real correct way of drawing this, but I'm going to do this here because just because it's going to be a little easier to visualize this. But we have A3. Now, in reality, this point does not point to a node. This pointer points to a BinTree object that contains a root pointer within it. But I just don't want to overcomplicate this drawing, but that's the idea. Now, of course, we can do the rest. So I'm going to go ahead and just quickly do the rest of these. So let me just, you have to one by one read in A and 3 and then keep pushing them back into our vectors. So let's see, I think we have 6 in total. So that's 3, 4, 5, and 6. Not really well drawn to scale, but good enough. So we have B4, C2, D7, E1, and F8. That's going to be our initial scenario. We're just going to just push back all of these binary tree objects, and they all just contain a single node in each of them. And we use the constructor to allocate that root pointer to each of these nodes. Okay. So it's given to you in the contents of main portion. I'm going to now talk about this. What we're going to do now, we have to find two objects whose has a minimal frequency. So right now, the smallest frequency tree would be this node right here. Now, how do we do that? Well, for example, if I were to say forest at index wherever, I'll say 0 for right now, arrow get frequency. That's going to return that tree's frequency, which is going to have the value 3. So I can do the same thing for forest 1, forest 2. So you're going to loop through everything in your vector and find the smallest element, which will be right here. That's going to be your smallest. So what you want to do now is you may want to create some pointer. So I'll just call this maybe just BinTree star. I'm going to call it smallest for right now. Equals, well, forest index. Let me just make sure I count correctly. 0, 1, 2, 3, 4. And you want to remove this from our vector. There is an erase function for vectors that can remove that from our vector. So we're going to remove this from the vector. So I'm going to, for now, smallest, I'll just put this here, smallest contains E1, just to kind of make things easier. So we're going to remove this. I'll try to see if I can scoot this over. But for vectors, very simple. Very simple to remove in a vector. There's an erase function built into the vector class, I believe. And now we want to get the next smallest element. So if you were traverse once again, our next smallest one will be C2. So we can just keep iterating through each element of our forest, arrow get frequency, and find our min. So that's a 135 problem, really. And our next smallest one will be C2. Okay, so we have another pointer we can create, possibly. I'll just say second smallest. And we locate the index of that position will be 0, 1, 2. And we're going to get that reference and store it into this reference right here, second. So second will contain the string, will contain the tree that contains C2. Then we want to then remove this from our vector by using the erase function. Very simple, and you can look up the code on this. Very simple to remove and scoot this over. Now, linked list would be a bit more efficient, but it'll be okay with the vector as well. But with the linked list, it requires an overhead to remove an element. In the vector, you have to remove it and have to scoot everything over, so it's a bit of an overhead, but it's not a big deal. I won't be so rough on that. So vector is good enough. So if you use a vector, you should be fine. So I'm having a hard time. There we go. Okay, cool. Okay, so now the result is the following. You have to just essentially insert a new element into this forest. So I want to go ahead and do the following. I have to combine these two together. Now I'm not going to give away too much of the help, but I can give too much away. But look at this constructor. Smallest would be your T1, and second would be your T2. They're both pointers. You can pass those into your constructor, which will merge these two trees together. And the result is going to be this. You want to have, let me just say, you want to have a node right here, which is going to be, it will contain some empty string right there, empty character, sorry. But you want to do this. You want to have E1 here, C2 here. And the frequency of the root is going to be 3, which is the sum of this node's frequency and this node's frequency. And then I'm going to try my best to sort of move this over. We want to then insert this back into our binary search tree. Or sorry, into our not binary search tree. Into our forest. So now what happens is we have to simply, we take these two pointers And we can use the constructor to essentially merge these. And it's very simple to merge these. All you have to do is just basically just combine them. So we create a new root, and then we take the smallest one on the left side and the second smallest on the right side. We link them up to a new root and return this object, and we're going to push it into our forest. And then what happens is we do this so once we have one element left in our forest, then we have our complete Huffman tree, but we're not quite there just yet. So our next step is you'd have to find our smallest element, which would be A3, is our next smallest. So I'm going to just erase all of this so I have some space to write over here. So again, all you have to do is traverse our forest and then constantly, return the frequencies and get our smallest one. So our smallest frequency would be here, A3. So we're going to now remove A3 from our forest and store this into a local pointer variable. Then we would remove this from our tree. Let's see if I can try to shift all this over to the left. Then we have to find our next smallest one, and it happens to be this tree right here. It's going to have the value, because this tree, the root of that tree, returns 3, even though it has these 2 leaf nodes, but the root node is going to have the value 3. So when we merge 2 trees together, we have to sum up these 2 roots, and then for the root of this new tree, we have to put the sum here. So if I were to call index 0, 1, 2, 3, so forest index 3 arrow get frequency, it returns 3 because 3 is the root node's frequency, which was the sum of the 2 previous leaves. So now what we do is you have to, again, remove this from our forest by taking the address of this tree and storing it into a pointer and removing it from our forest. And now we have to combine these two. So again, this will be T1, that'll be T2. So we can, of course, now can merge these, and the result is going to be the following. It'll be empty, and then we have 6, which is a sum of T1's frequency and T2's frequency. And this new node, this new root, we're going to attach its left and right to those 2 and put this back into our forest. And then we continue. So our next step, we got to find our smallest frequencies that are available. So our first one will be B4. So we're going to first traverse our forest and then compare these frequencies. We get B4 is our smallest. And then, of course, we can slide everything over to the left. Our next smallest, mostly it's going to be this tree right there. So we can, of course, remove this from our forest by just storing the address into a temporary pointer and removing it from our vector. And now what we have to do is, this isn't my T1, that's my T2. These are my 2 objects. And I essentially, inside that constructor, I build a new root. Its character will be empty character. I add the frequency of T1 and T2's root nodes, 4 plus 6, so 10. Attach these 2 accordingly. And then I push this back into my forest. Running out of space here. I think that should be good. Okay, so now we're not done because once we have 1 tree left, then we're done. So again, we have now remove our 2 smallest frequencies. So it would be D7, then F8. So I'll just go ahead and sort of just take these 2 at the same time. But you would have to go through it and do two lookups. You gotta find the 2 smallest elements. So of course, in this case right here, we would essentially, this is my T1, that's my T2, and we're going to have to, pass these into our constructor, link them up. This would be an empty character because it's not going to be a leaf node, and we add up their frequencies, 15. And we sort of push this back into our vector. And now, at this step, we have 2 more elements left. We have our smallest one, which our smallest root will be the value 10. So we're going to go ahead and remove it from our vector. And we're going to store the address of that tree into a temporary pointer. And then we're going to grab this one next. And now we're going to, this is my T1, that's my T2. And we're going to pass those into the constructor. The constructor is going to build a new root. The character will be empty. We're going to link the left and right accordingly. And we're going to add their frequencies, which will be 25. Oops. And then we're going to push this back into our forest vector. And now we have only one tree left. And this is going to be our Huffman tree. So essentially, we one by one, all we do is we get the smallest frequency to root tree node, or sorry, our smallest frequency tree. Then our second smallest one, we store those into 2 local pointers, and then we're going to pass those into our constructor, which will construct a new root, and it will link those 2. This will be my left tree, my right tree. I allocate a new root. The frequency will be the sum of T1, T2's root node frequencies, and you push it back into the vector. We do this until we finally have only one element left in our vector. This is going to be our Huffman tree right there. So let's go ahead and go over how do we actually get the prefix code from this tree. Let's go ahead and begin with that. So let's go ahead and first do a high-level view of this. So basically, if you look at this tree from the root position, we can go left or right. So the left direction is going to be 0. Right direction will be the character, or going to be the bit 1. Let's go ahead and do this. So we have essentially 0, 0, 1, 1, 0, 1, 0, 1. So in this case right here, B is going to be a root node. So B's prefix code is going to be 0, 0, because we went along this path to get there. And this path essentially had a 0 and a 0. So that's how we get B's prefix code. Now for A is going to be 0, 1, 0, because we went this path, and then this path. So it's 0, 1, 0. And then for, let's see, for E, 0, 1, 1, 0, 0, 1, 1, 0, because we went this path, this path, this path, this path. Notice that since E's frequency is really small, that means that E doesn't appear too much in the string. So then we want to use maybe more digits to represent that. But we will see in a second how the rest of these go. So let's go ahead and just resume. So for C, it'll be 0, 1, 1, 1. So 0, 1, 1, 1. And then D will be 1, 0. F will be 1, 1. So notice that all the, so for example, for characters D and F, since they have larger frequency values, they're going to have a fewer amount of prefix code. Only 2 bits are needed to represent D and F compressed. Whereas since you can see here for E and C, even A for that matter, these have a lower frequency, so they're going to have more bits, which makes sense because we want to have fewer bits for the higher frequency characters and more bits for the lower frequency characters. So the question is, how do we construct this? So we can use a prefix or postfix traversal. So either is going to be pre or postfix. So you have to use the function get prefix code. So for example, in our forest, let's suppose we do the following. I want to say maybe string prefix, and we can do prefix equals, let's say in our forest, at index 0 is going to be our final tree, arrow get prefix code, put on 2 lines, about a space here. Let's say I pass in like E, for example. This function has to return the string 0110. So it has to first find the letter E in this. So it's going to be fairly similar to that find function on binary trees, except once we hit E, we have to kind of return characters up the tree, essentially. So the parent knows which path we took, the left or right path. So this might be a postfix sort of construction. But once we hit E, return to the parent knows it returned sort of, you have to tell the parent that, we found this child on the left side, and the parent, we can construct, essentially, you can concatenate these characters in reverse, if you will. But I'm not going to really give away too much on that, but you'd have to traverse this tree, and most likely you'd have to, so based on the function prototypes here, actually, yes, you'll have to actually construct this in post-order fashion. So I'll just give that away to you right now. And it returns a string. So essentially, it returns partial strings up the tree. At the very end, we get our final result. So it's going to first return, I'm not even going to say anymore because I don't want to give it away. But this is the idea. We got to find the leaf that matches the character, and then on the way up, we have to essentially build this tree, or build this prefix code in reverse, is the idea. So of course, you want to do this for every character. So you want to essentially, you want to get the prefix character for A, B, C, D, E, and F, and you want to store those into some kind of a structure. So I would suggest, now we could use unordered map to do this, but we haven't covered that really in 302 just yet. So I would suggest maybe having a two-dimensional sort of string array where you can have essentially this. You can have essentially A in the first column, and then A's would be 0, 1, 0. And next row you'd have B, and then next row, its second column would be B's prefix code. So you'd have 0, 0 for B, and so on. So two-dimensional vector where the first column will be the letter, and next column will be the prefix code, or vice versa, it doesn't really matter, but you want to essentially, for each row, you're going to store the original letter and a prefix code. So using this, we'll be able to actually easily output each letter's prefix code in our program, and we'll be able to read in the string that contains the compressed file and sort of try to match our prefix codes to a string read from the file, and then be able to return or be able to output the letter that represents it. So similar to our first example. So we can try to move this over to the left a little bit. Nope, I think it's Control Shift, I believe, does that. Perfect. Okay, perfect. So over here, for example, you want to have a two-dimensional array. So as we read these in, we constantly match it with our prefix codes. And once a match is found, okay, return that character. That's going to be the character of the original character represented by that prefix code symbol. So that's kind of what we want to do. You want to store all of those so that way we can easily look these up. Now, using a map would be actually much more efficient because you have to linear search this over and over as you decompress the original text, whereas a map would be much faster. But since we haven't covered maps in class, and some people might know about maps, it would give certain students an unfair advantage. So for that reason, we're going to have to all just use a two-dimensional vector to store all of these. So this is the idea, the concept of how we want to, given our characters and their frequencies, how to build the Huffman tree, and also how to construct each character's prefix code. Let's go ahead and now go over the input output, and I'll do some sample test runs as well in this video. Okay, so I discussed essentially contents of main already. Of course, you can read through that, and of course, you can go back and play back the video for yourself. But let's go over the input and output in this program. So in this program, since we're going to have multiple input files, we're not going to be doing input redirections. So we're going to use command line arguments to do this. And essentially, I'll go over that idea in a little bit. But I want to first just go over the input files. So the first argument you're going to be given will be this file called letters.txt. And this file contains every letter mapping to its frequency. So this is going to be letter A, frequency 83. Letter B, frequency 86. Now, I used ASCII symbols, not the actual characters in the input file, because I think I think what I do is I use some white space characters also. So a space character and a new line, a line feed, is also going to be used in our encoding. And I'm not sure how to represent that in a text file. And also, I don't like using getLine too often. I like using the input extraction operator. It's so much easier to work with that. So for that reason, you'd have to essentially read in this number and then typecast it to a character so you know the actual symbol, and store that into a character variable, and it's going to be the frequency. So you want to first go through one by one, and each of these will be a single node. So you're going to read in that number, you can allocate a new binary tree object, and each object will have only one root node, and this is going to be the character 98, frequency 86, then character 99, frequency 77. So you're going to essentially have 30 binary tree references onto your forest vector, and each of these references refers to an object that contains a single root node with the character frequency respectively. So it's going to be a first step. Now, your second input file, which is optional, is going to be, let's look at so here's the Gears of War. So a lot of ones and zeros there. So it's going to be our compressed file. We're going to have to decompress it. And the result would look like this if you correctly decompress it. So this is basically just a backstory to the Gears of War game. It was a pretty great game back in 06 when it first came out, and the newer versions were always nice. Now Gears 4 and Gears 5 have really great, they're very polished games, but it's missing the soul. That game has no soul, really, Gears 5, but it's a very polished game, so the multiplayer is pretty fun, but really it's missing that element that the original Gears of War games had. They also have Resident Evil 3, decompressed, and then decompressed Resident Evil 3. So your output should be this. It's going to, of course, on CodeGrade, it's going to match this up. And of course, this is the original Resident Evil 3, the good one, not the remake, which is a travesty to say the least. But anyway, there we are. So I give you guys the binary tree header file. Here's the implementation file with the functions you have to fill in the blanks, and the main is also given to you. And here's our arguments. Of course, we'll go over how that works in a second. So the idea is we're going to have, at most, we're going to read in two input files. So in the contents of main, I think also in the output I say it as well, the idea here is if your program only gets sort of two arguments passed in, then in that case, you are not going to be reading in the actual compressed file. You can read in just the letter frequency file only, and your program has to just simply output each letter's prefix code. The purpose of that is that way we can have more test checks in CodeGrade, so you can of course validate and make sure that your prefix codes are coming out correctly before you try to actually decompress the file. So definitely helps. At least if you're getting the correct prefix code, then you can feel pretty good about the rest of the way. And if you give in two input files, so 3 arguments in total, then you're going to basically, you're going to be given a compressed file, and you have to go through this. And using your prefix codes, you have to essentially determine where, the prefix code cuts off, so you know exactly where to start outputting the actual original characters. So anyway, let's go ahead and run this and then talk about what do I mean by a command line argument. Okay, so to compile this program, you would have to just use G++ main.cpp and then BinTree.cpp. There we go. So now to run this program, you would do /a.out. And then if you want to pass in a file name through a command line argument, you just, of course, put it right here. So letters.txt. So in your main program, essentially the way it works with command line arguments is that you have this argument vector right here in your parameter. So argv0 is always going to be the string that contains /a.out. Oops. That's always going to be argument 0, argument 1. Or sorry, argv0 always contains a.out. And then argv1 is going to be a next argument on your command line, which in this case is going to be letters.txt. Using argv1, you can, of course, assign this to a file stream to open a file stream, and then you can read through that file. Now, in this case, if you're only given 2 arguments, so if args equals 2, that means you're only going to have 1 input file. In that case, you're going to build your Huffman tree, and you're going to output the results, output the actual Huffman code, output the actual prefix code for every letter. So I have in mind where it says A maps to that prefix code, B maps to this, and so forth. Now, for space, I actually output the string space, literally, because otherwise it puts a blank space here, which is sort of not readable. And then for return, it would output a new line by itself. So I put the actual word return over there. So you have to, of course, as you go through your vector, once you hit the space character, then you want to maybe see out the string space, not the actual space character stored in your two-dimensional vector. Now, dot and comma, it's good enough. If you read a character that contains that /n, which is the new line character, you want to maybe output the string return. So that way it tells you what's going on. But you can see here, this is going to just, in this case, it will not actually try to decompress anything. It will just simply give you the outputs. This is a good way to test to make sure that we are correctly getting it. So we're going to check this on code read as well. And then if you wanted to actually decompress the file, you can, of course, do letters. And I'm going to put in maybe Gears of War compressed. So in this case right here, in this scenario, argv0 would be a.out, argv1 would be letters. In this scenario, however, argv2 contains the string Gears of War compressed.txt. And of course, you can have an else if case. So else if args equals 3. If that's the case, then you're going to have a different part. You're going to have a different phase. You're going to have to, of course, still construct your Huffman tree and construct everything, construct your prefix code. But then instead of outputting your prefix codes to the screen, you're going to use those prefix codes to decompress this file. Let's see what happens here. And there's the original text. And the same thing I do for Resident Evil 3. I can also do RE3 compressed. And there's our complete compressed file, right? Our original text right there. But if you notice, for Gears of War compressed, a bunch of zeros. For Resident Evil 3 compressed, a bunch of zeros. And of course, the program compute or constructs this original output, which is actually, you can look at this here. I also provide this for you on Canvas, the original output you can test with, but it's going to compare this on code grade. So on code grade, we just simply have, again, our usual checks. Make sure you have comments, you have header comments. It will check for memory leaks as well, but that shouldn't be a big issue in this program. It will check to make sure that your prefix codes are correctly constructed, and also has some checks that will make sure you actually were correctly able to decompress the file ones and zeros into the original file like this. So anyway, that's it for this video. So hopefully this gave you some help or somewhere to get started on the assignments. So I guess happy coding, and till next time.